So in this topic of melting and boiling point, we are actually bifurcating pure and impure substances. When I say impure, I'm actually talking about mixtures, since the key point also tells you that mixture is not a pure substance. If a sample contains only a small amount of any unwanted substance, we can call it an impurity. And there you go, you can call the whole thing a mixture. So when you talk about pure substances, like let's take example of pure water, right?
Mm.
And on the other hand, let's take example of mineral water. Mineral water is the one that we commonly use to drink, right? We do not drink pure
Yeah.
water since pure water is not good for drinking. The water with dissolved minerals and salts is actually very healthy. So we need to drink
Mm.
that. So pure water has a melting point of 100 degrees, 0 degree centigrade, which means the ice melts at 0 degree centigrade into water, or the water freezes at 0 degree centigrade back into ice, right?
Mm.
And in case of boiling point, it is actually 100 degrees centigrade. So the pure water would boil exactly at 100 degrees centigrade. Now, if we talk about mineral water, and he actually has taken a little bit different of an example, he dissolved 10 grams of carbon table salt, the salt we eat every day, which is actually sodium chloride, in 1 liter of water. And then he has talked about its melting point. So let's assume we have the same mineral water. So the melting point would be around minus 0.6 degrees centigrade. And the boiling point would be around, as stated in your book, is going to be 100.2 degrees centigrade. Now, what would you understand from this specific point? From this specific point, you'd understand that the value would be less than the original melting point, and the value would be more than the original boiling point. So what we can understand is that the melting point is lowered and the boiling point is raised when we add an impurity to a liquid. All right. So the melting point is lowered and boiling
Can you
point is
repeat that once
increased.
again?
The melting point is lowered, like written over here, and the boiling point is raised, like written over here, for a
Yes.
liquid whenever an impurity is added.
Oh, okay.
Right? So
Mm.
what if we get the information like melting point or boiling point in exams, and what are we going to assume from it? It doesn't just go for any liquid, it actually goes for any solid, it goes for any gas, it goes for anything that is under discussion as a term of state of matter, right? So
Mm.
since we were only talking about a liquid over here, so that's why I said so. You'll notice that we took an example of aspirin over here. Now, aspirin is commonly known and marketed by many names like Disprin. Disprin is a common headache tablet around the world. This is the most common marketed name of this medicine around the planet. All right. So
Mm.
aspirin is actually a molecule, and we know that it is a white powder that melts exactly at 138 degrees centigrade, since it's a pure substance. If the melting
Mm.
point of your sample, which is said to be aspirin, is melted in a range, it is quite impure. All right. If
Oh,
it does not
okay.
melt at 138 degrees centigrade, actually it melts any temperature lower than 138. Let's say it melted at 137, or in another example, it melted at 136, or it melted at 130, or whatever. You would know that if it doesn't melt at exactly 138 degrees centigrade, it doesn't melt over there, it melts at any of these temperatures, you'll instantly get to know that the sample is impure, that aspirin in
Yeah.
that case is not pure. If it was pure, it
Yeah.
has to melt at this exact temperature. That's why I was using the term sharp melting point or sharp boiling point, right? This is the term which explains to us that if the substance is pure, it should melt exactly at its melting point and exactly at its boiling point, and nowhere else.
Okay.
And if it's
So,
Mhm.
by seeing the melting point, like if it's having like sharp one, and if we try and it melts at the correct like given value, then it is pure, right? But if
Right,
melts like around the like, for example, as you said 38, so if it melts at 36 or 35, I mean 135, so it will be impure, right?
right, exactly.
Okay.
Remember, melting point is lowered, so you can't take a higher value. As soon as you're going to add an impurity, remember, it won't melt at 139 or 140. It would always melt lower than that temperature. Since melting point is always lowered, as mentioned over here, or boiling
Mm.
point raises. Right? So you can't take
Okay.
an example of a higher temperature. You need to take an example of lower temperature in case of melting point.
Okay.
Good enough?
Yes.
Can we move on? Separation of mixtures?
Yes.
All right,
Yes.
let's clear it all up and let's move on. So yesterday I was saying separating mixtures is extremely important in chemistry. We are going to see the processing of crude oil in the last chapters of this book, or producing fresh water from salt water in other chapters of the same book, or enrichment of uranium to come up with producing electricity from nuclear power. In forensic sciences, the components of mixtures have to be separated before they can analyze. We may be able to analyze a sample of blood or a sample of hair or a sample of muscle or maybe any other samples from any parts of body for forensic science purposes. We do the same for clinical sciences purposes, medical clinical mix
Mm.
purposes, right? Since they're very much needed when you're going to go for a medical examination. So chemistry is very
Yes.
much involved into that. And we are right now going to study different kinds of techniques, and every technique would have their pros and cons, and every technique would be used in a specific scenario. As soon before we start with any techniques, as soon as you see the name of that technique, the first line would always be about a scenario, which scenario you're supposed to use it in. All right.
Okay.
And after
Yes.
explaining the whole apparatus or the procedure, how we use that, or different terms that are needed in that specific experiment, by the end of that experiment, I'll always discuss the pros of that specific technique or the cons of that specific technique. All right. Although that's not
Yes.
mentioned here in the book, but since the book is just going method by method, they're not comparing them, and the student is supposed to compare them when they come as a part of the paper, or student is supposed to know which technique to pick as per their pros or cons, or as per the specific scenario. Since the scenario is mentioned in the very start at every time, it's not difficult for a
Mm.
student to pick up or predict a technique in a specific question. But since these two are not usually mentioned along with the process, so I am going to explain, and make sure you have the book ready, a pencil ready, so that you can keep writing
Yes.
this stuff. It would be easier for you to pick these processes or knows about the goods and bads or ups or downs of these processes. So let's start with the very first one. The first one is filtration. It's one of the easiest processes. It has the least learning curve, right? So the pros are it is easy, less learning
Like
curve.
pros means like what does it
Advantages.
means like?
Pros means
Oh, okay.
advantages. All right. Okay. So
Okay.
what I'm gonna do is that instead I'm gonna use the word advantages exactly. All right. So
Yes.
advantages of this process is that this is an easy process. Easier processes are
Yes.
usually liked all around the world since anyone can carry them out. Maybe I'm a teacher, I'm used to it, so it's easier for me. But when I use the word easy, it really means that anyone can do it. Even a student
Hmm.
or a researcher or a scientist or a teacher, anyone can do it, right? So filtration,
Yes.
this exact specific scenario is to separate a solid from a liquid.
Hmm.
For example, sand can be separated from water by filtration. Now, here, what I'm going to do is that I'm going to improvise it a little bit, and we are going to go for insoluble solid from a liquid. all right? Since sand is
Mm.
actually an insoluble solid. If the solid was soluble, you cannot separate it. And
Okay.
that is also mentioned over here. Okay, so
Mm. Yes.
sand can be separated from water by filtration. The apparatus is as shown over here. Let's look at the apparatus. This is known as a funnel, and it has a filter paper. We actually add the filter paper to it after folding it in V shape, right?
Mm.
And then there is a beaker at the bottom. This beaker is usually filled with filtrate. You know, some specific terminologies written over here. Apart from the other words that you may already be familiar with, you might already know what a funnel is, or what a filter paper, or what
Yes.
beaker is, what sand or water means. But these are the exact terms that comes with this apparatus, and we need to explain them. So whichever is the
Mm.
substance that is left on the filter paper, we call it residue. Whichever substance is that. In this specific scenario, that substance is sand. So sand is the residue in this case. And the liquid that comes through is the filtrate. So water is the filtrate in this case. So every time,
Mm.
whatever you get at the bottom, whatever passes through the filter paper is the filtrate. Whatever cannot
Mm.
pass through the filter paper is residue. Now, let me explain a little
Mm.
bit of prerequisite. The filter paper is a paper which has very small holes or pores in it, right? We call
Mm.
these holes as pores. This word comes from biology, right? So
Yes.
very
Yes.
small particles can actually pass through it, and larger particles cannot pass through it, so they stop right on it. So the sand has larger particles which were not able to pass, so they stopped on the filter paper, and we call them residue. Water particles were smaller in size, they were very easily able to pass through the filter paper or the pores of the filter paper, we call it filtrate. So the same thing would happen to anything that passes through or stays behind, respectively, for filtrate and residue.
Okay. Yes.
Filtration can be used to separate two solids. Now, this comes as a pretty good point from each other if one of them is soluble and one of them isn't. All
Mm.
right.
Okay.
So if we
Yes.
have an example of sand and salt, now sand would become the residue and salt would become a part of filtrate, right? Why is that so?
Yes.
That is because sand is actually insoluble. So anything insoluble will stop on the filter paper as a part of residue, and salt is filtrate because it's soluble in water, right? Which gives us the idea
Yes.
that if anything is insoluble, you're going to make it as residue. And if anything's soluble, you're going to call it a filtrate, since that would be able to pass along with water all the way into the beaker, right?
Mm. Okay.
From here to here
Yes.
in the form of drops. Okay, so let's
Mm.
come to the advantages, and I am going to raise a little bit of this in order to be able to write my advantages and disadvantages. It's an easy process. It's actually pretty inexpensive one at that, since the stuff you require, the funnel, the filter paper, the beaker, they are very inexpensive, right? And when it comes to disadvantages, when I would use the word cons, it actually means disadvantages. Disadvantages
Yeah.
that it takes time. It
Okay.
is easy, it is inexpensive, but it takes its time. At the start, the filtration is going to be a little bit faster, and it would become slower with the passage of time, and would become really irritatingly slow at the end, towards the end of it. So sometimes you
Mm.
need to wait for like 15 minutes, maybe 20 minutes, maybe half an hour for the whole process to complete. Bigger the volume of the substance you need to filter, the more the time it is going to take. All right.
Okay.
So
Yes.
that's why we call it as a disadvantage of this process.
Do they
That's
ask
about it.
this in exam?
No, they don't ask the advantages and disadvantages. They are never going to
Mm.
ask it directly. What happens is that for any specific system that you need to separate, you need to keep the advantages and disadvantages in mind, and then you're going to choose among the processes. Now I'm going to teach you
Okay.
a lot of processes like filtration or crystallization, and then I'm going to give you a scenario. In that scenario, you're going to consider that what kind of stuff am I going to separate? Do I have more than one kind of processes to separate the same for the same scenario? So which one I should choose? Should I choose in this specific scenario? That is the kind of question. That's why you need these advantages or disadvantages.
Okay, what about the like labeling? Like if they gave us the diagram and we have to label, right?
Yeah, labeling is also a part of question. And but those are
Okay.
easy questions since the students quickly understand which one's the funnel, which one's the beaker, the filter paper, residue, or filtrate. Since these
So
are the Mhm.
they give us like materials, for example, as you gave sand and water, and we have to find which process is used, right?
Right, right.
Oh,
We're going to
okay.
come up with different examples to for your practice, and then I let you know what substances or what scenario you have, and then you are going to pick which process is going to be the best possible one for separation. Since we have many separation techniques, so it differs from process to process, which process can be chosen in a specific scenario and why. And
Yeah.
these three things are going to help us. The scenario, the advantages, and the disadvantages are going to help us choosing the right process for the right question.
Yes.
All
Okay.
right. So I'm going to clear it up and we're going to move to crystallization. Since as soon as you go with the second process, you are able to compare how these processes actually differ from one another or which one is going to be better in which specific scenario. So let's clear it all up
Yes.
and let's move on to crystallization. Crystallization is actually somewhat a longer process. Crystallization is usually told in a paragraph, but I most of the time I tend to ask my students to convert it into points or steps for this process to be completed. Now, crystallization can be used to separate a solute from a solution. Now, this solute can be soluble, and since the previous one was about insoluble solid, this one helps us for soluble solid. All right. So uh,
Yes.
it's all right if you write soluble solute from a solution, a little bit of improvisation in the first line, writing soluble before the word solute. All right. For example, it could be
Yes.
used to separate sodium chloride from a sodium chloride solution. Now, sodium chloride is soluble in water. What do we do? The solution is heated in an evaporating basin to boil off some of the water until almost saturated solution is formed. This can be tested by dipping a glass rod into the solution and seeing if crystals form quickly on its surface whenever it is removed. So what do? We actually take a lot of salt and some of the water, a lesser amount of water if possible in comparison of the salt, and we start heating it up. We are doing it so that our first step can be taken, and our first step is forming a saturated solution. Now, in order to form a saturated solution, we heat it up a little bit so that we can do it quickly. You do understand that heating up a system allows the system to dissolve more of the solute, so the saturated
Yes.
solution will be quickly formed. How do we test a
Hmm.
saturated solution is formed? We test it by dipping a glass rod into the solution, and as soon as we take out the glass rod, the crystals form on the glass rod pretty quickly as soon as we take it out. If the
Yeah.
crystals form quickly, the solution is saturated. If the crystals take too much time, the solution might need a little bit of more solute. If the crystals do not form at all, you need to either heat it more or add more solute, both of these. So as soon as the saturated solution is formed, the Bunsen burner is then turned off. The crystals are allowed to form as more water evaporates and the solution cools. So the crystals can now be removed from the mixture by filtration. So what did we do? We formed a saturated solution and then we heated that solution to boil off some of the water. So the
Yeah.
next step can be written as evaporation, or we might say it as some boiling. You don't need to boil all of it. That's why I use the word some boiling, or boil off some of the water, right?
Okay.
And then
Yes.
in the third line, or the third step of the process, let the solution cool, or in terms, let it get dry. All right. Now, if you
Yes.
allow to cool the solution, the hot water automatically evaporates. You don't need to heat it. So they automatically evaporate. And what happens when the water evaporates out of it? It becomes dry. So whether you use the word dry or you use the word cool, it is all right to use any of these words as a third step towards it.
Okay.
The crystals can now be removed from the mixture by filtration. So the fourth step can be filtration, right? What can we do?
Yes.
We can filter the rest of the solution, right? And we can simply get the crystals. So sometimes,
The point which you said that if the crystal will be formed as we dip the rod, so what will be that called?
that is just testing whether the solution is saturated now.
Oh, okay.
All right. How do we test that the solution is saturated? We can't do anything else apart from dipping a glass rod and seeing if the crystals are forming quickly on the surface whenever it is removed out of it.
If it's not forming quickly, it'll be unsaturated, right?
Right. You either need to add more solute or heat the system a little bit more. Either of these options.
Yeah. Okay.
Okay. So are we clear with the
Yes.
steps?
Yes.
Good, good. So remember, this process is for soluble salt. The previous process was for insoluble salt. This process is for soluble salt, right?
Yes.
Okay. Apart from that, advantages, it can be carried out for soluble salts too. It gives you pure crystals of salt, right?
Mm.
And disadvantages, multi-step process. Seriously, that's not a disadvantage, being a multi-step. So you can say there are no disadvantages to this process. All right, we do not consider multi-step as a disadvantage. I only tell that to my students since uh, almost more than a decade ago. A question related to this step was there in Cambridge and in
Mm.
Edexcel. So yeah, it's pretty old. We don't consider it as much. You can say it's now obsolete. All right, it's not used anymore.
Yes.
So really, there isn't a disadvantage. It's just an old piece of information I wanted to share with you, just so you know. You're not going to use it in exams, though. All right.
Yeah.
Good, good. Can I clear it up? Can we move on?
Yes.
Okay, I hope you're familiar with all of the apparatus. This is a tripod stand. Tripod stand is usually drawn with two legs. Actually, it has three, as the name suggests, tri. All right. We have this
Yes.
gauze. The gauze is there for uniform heating. Then we have an evaporating basin and a glass rod. I hope you're familiar with all pieces of apparatus, right?
Yeah. Now I came to know the more, but some of them only I knew. Okay.
Okay. If you don't know about any of the pieces of apparatus in any of the drawings, please ask straight away, because I sometimes assume that it's an easier piece of apparatus. You must be familiar with it, but I don't exactly know. So if I forget or if I skip doing this part, please do ask so that I can explain
Yeah.
it to you. All right. So I'm going to clear
Yes.
everything and we're going to move on And we're done with crystallization. So where is crystallization applied? Filtration and crystallization are usually applied to obtain pure salt from rock salt. Rock salt is actually contaminated by various earthly or rocky impurities. These impurities aren't soluble in water. When I say earthly impurities, I actually tend to talk about soil, since we dig it out of the earth. So soil is a definite part of it. It is bound to come along with the salt, and then sand, and then some pieces of stone, or stones can also be considered as gravel, or can also be considered as silt. So we get many kinds of earthly particles or impurities along with it. So we only
Mm.
eat salt. We don't eat any of these impurities, and they are not
Yes.
insoluble in water either. So what do we need to do? This definitely requires a separation technique.
Can I say?
Hence the words crystallization and filtration. Yeah, go ahead.
I'm not sure, but we should first like crush it down, and then we have to like dissolve it, and then filter, and then crystallization. Is it correct?
The steps, the steps for making
Yeah.
pure salt from rock salt.
Yeah.
Can you repeat the steps again?
Okay. So first we should crush it down,
Right, good.
and then dissolve it,
Right, understandable.
and then filter,
Correct.
and then crystallize and crystallization.
Right, crystallization. Why do you think crystallization is written? Since after filtration, you'll need to go with evaporation and then cooling and then filtration again to separate the crystals. Hence the whole thing,
Mm.
crystallization. So sometimes we
Yeah.
need to use filtration and crystallization along with one another in order to complete a process. All right?
Yeah. Mm.
Good, great. If you understand that already, let's move on. Simple distillation, the next step. Now,
Yeah.
which process we choose actually depends really upon which substance we are interested in. Now, previously,
Mm.
I've been talking about that you can separate a soluble salt. It's happening, just a second. Okay, you can separate a soluble salt from water, and previously, all our efforts were there to get the salt. We were interested in getting the salt. We were never interested in getting the
Yes.
water. In case of
Mm.
seawater, we might be sometime interested in getting the salt out. We can use the salt,
Mm.
or sometimes we might be interested in getting the water,
Yes.
right? Like
Yeah.
UAE and Saudi Arabia are the countries which are using seawater, and then they are converting
Mm.
that seawater into both salt and water separately. They use the water for drinking and other purposes, industrial or domestic, whatever purposes are those, and then they use the salt
Mm.
again for different purposes. You may use the salt domestically for eating, or you may use the salt in industry for different other purposes. So actually, we
Yes.
might be interested in any of the things. Now, what we are interested in totally changes our choice of the process. If we are interested in salt, we might go with crystallization. But what if we were interested in water all along? If we're interested in water, this should be your choice. Crystallization shouldn't be your choice. Why? Because during
Mm.
crystallization, we evaporate the water off. We're not interested in water at all. But in
Yes.
simple distillation, we won't be interested in salt. We will definitely be interested in water. So what we are going to do is that we're going to save water all along. And that's what you'll see
Mm.
happening in this simple distillation. So let's go through the process. Simple distillation is the process in which we separate the components of a solution. Although we use crystallization to separate sodium chloride or salt from the salt solution, we can also collect water if we use simple distillation. That's what I just cleared. Now, what happens in
Yes.
the process is that we boil the water, it evaporates, or it is converted into steam or gaseous phase, but then we condense it back by cooling it down into a liquid. And the part of apparatus that is going to do that is known as condenser. You'll see the condenser over here. This big piece of apparatus is actually a condenser. It is going to condense the boiled water or steam back into water by cooling it down, and the salt remains in the flask. Now, this is actually a better process. Why? You get the salt as well as you get the water. Okay. Now, we're going to
Yes.
start the process from understanding from right here. We have the gauze, we heat it up, we have the sodium chloride solution. You can directly take seawater, that's fine. You have a side down flask, but you close it from top, all right? And then you use the whole condenser for cooling the water, and then you get pure water over here. What happens actually in this process? When you heat it, the vapors of the water get up. Since gases are lighter than liquids, so they go all
Yeah.
the way and they go through this and they come to this part. Now, condenser has a separate two outlets. One of them is water in. A simple tap water goes in, and the same tap water comes out of from here. When the heated particles, the heated gaseous particles, you may call it steam, you may call it water vapors, when they go through this, they actually exchange their heat. What happens is that they cool down and convert into water drops, and this water that is coming out becomes hot water. We actually send cold water in and we get hot water out because it takes up the heat from these vapors, and they actually exchange the heat. The vapors become water, and the water becomes hot water. The tap water was actually converted into hot water.
I did not understand this.
Okay, there is something that we commonly do in during the harsh winter. We actually like hot beverages a lot during harsh winters, right? Name the hot
Yes.
beverage, coffee, tea, whatever we do, we really love it during harsh winters. And not just the taste or the flavor or the choice of the beverage. Sometimes you'd see that people have those cups or big mugs, and they like to wrap their hands around the mug in harsh winter, since that also heats
Yes.
up your hands, right? And it's a really good
Yes.
feeling at that time. What is actually happening around it? The heat from the mug is actually warming up your hands, and in those harsh
Yes.
winters it's a really good feeling, right? So what's
Yes.
happening is that we have hot vapors in here, and these vapors are actually heating up this cold water. When they heat up the cold water, they themselves cool down. When they cool down, they fall in the form of drops over here. We call it heat exchange. Heat was exchanged from one part to another part of the system. Similar when coffee exchanged the heat through the mug all the way to warming your hands. Make sense? So these
How does the
get
water, how like it's written right, water in. So how does the water goes inside?
yeah. I'm gonna pause the resume recording. Now you'd notice that this is the condenser. Okay, this is the condenser. And I don't know the video, why the video is not pausing. Oh, it paused. Okay, good enough. Now I am going to annotate on my screen. Okay, can you see the mouse? The hand?
Yes, but it's getting stuck.
Yeah, that's probably because I have a lot of apps working in conjunction with Chrome. Okay, so I have actually paused the video. Now, what you are seeing is the condenser right in front of you. You would notice that the condenser has two outlets, and they are actually
Yes.
connected with pipes. So you'd see that the condenser actually has the same pipe going around inside, and then there is another outer glass pipe. The outer glass pipe just holds the water coming from the tap and going back to the drainage or the same tap. All right. So the
Yes.
purpose of that water over there is only to come and go and just exchange the heat.
Mm.
Make sense?
Yes.
Okay, this video might not be as good enough, so I'm going to go back to a previous video. I'm going to stop the sharing for a quick minute. And now, can you see my screen now? This is a
Yes.
much better picture. Now, this picture actually gives you two different colors and lets you know that there are two different types of glass pipes in there. The original
Mm.
pipe stays the same and it does not mingle with the water coming in, out from, coming from the water in source from the tap or going out to the drainage. Can you see the two different pipes, one with white color with the purple arrow coming in and the other ones with
Yeah.
blue? The blue ones have the tap water, and that water is only coming along to exchange the heat, right? And then there is an
Mm.
inside pipe which does not allow the vapors to interact with the outer ones, since there is a glass wall
Yeah.
in between, just like the mug. So this black lining for the white pipe is actually acting like a mug. So the coffee does not
Yeah.
directly interact with you. There is a mug in between, and only the heat comes out of it. So those vapors do not directly interact or mingle with the water outside, the tap water outside, which is drawn as blue in this diagram. It only exchanges the
Yeah.
heat. And when it does,
Yes.
it can come in the form of drops. I've just played the video. You'd notice that it goes all the way from there. And that's how this works. Hollow section plus cold water gives you all the idea. I'm going to send this entire video to you. This is going to discuss separating liquid by distillation, and he's going to discuss a lot of good points in there.
Okay.
All right, good,
Yes.
good. So I'm gonna pause the sharing again.
Yes.
Good, good. So now you know that the water is going in and out of the condenser. Now, there are a few
Mm.
points that we need to understand. So I'm going to go through those points. Of course, you'd collect the salt from the solution as well as collecting pure water, since the salt would remain over here by the end of the experiment. And by the end of the experiment, you'll get all the pure water over here. Why do you
Yes.
have pure water? Because among salt and water, only the salt vapors would rise up and go pass through this. The salt, sorry, the water vapors will go up and pass through this. The salt will stay at the bottom. All right,
Yes.
good.
Yes.
Now, sodium chloride eventually becomes so concentrated that the salt will crystallize out. You'll have the crystal of the salt at the bottom by the end of the experiment and all the water over here. Now, there is one very important point that we need to understand, and that's written over here as a key point. Notice that water is
Mm.
always fed into the condenser from the lower end, hence
Mm.
an upward arrow. That way it fills this jacket, all this jacket, fills it up, and then overflows out of it. Do you understand what the word overflow means? Overflow means when the
Yeah.
whole utensil is filled and it just drips outside. That way it fills the condenser jacket better. If you did the other way around, if you go, water should go in through that and comes out from it, water will simply slip or slide all the way through without any exchanging any heat. All right.
Mm.
If you do it like this,
Yes.
the other way around, what's given in the book, the flow of water stops for any reason in the condenser, the jacket remains full of water. This also comes as a safety instruction, not just for an efficient heat exchange, but also for a safety instruction. Why? Because if the hot vapors come in contact with the glass all the time, they might be able to crack the glass because the vapors are at a very high temperature. If there is water around it, they won't be able to crack the glass, since they will always be able to exchange the heat with the water in the jacket. The outer blue portion is actually the jacket,
Yes.
right? I hope
Yes.
a simple distillation is clear.
Yeah.
Simple distillation is more advantageous than filtration or crystallization, since you'll know and understand that we're getting both the pure salt and the pure water out of it by the end of the experiment. We weren't getting
Yeah.
water at the end of crystallization, all right? But we do get pure
Mm-hmm.
water and pure salt by the end of the experiment. If not the pure salt, it can be a mixture, but the water would always be pure. Since seawater is
Okay.
already a mixture of many salts, since I started off with the example of seawater, you won't get just one single salt, but a mixture of many salts in there. But the water would be pure,
Yeah.
definitely. And the same process is
Okay.
being used by many Arab countries in Middle East, like UAE, like
Yeah.
Saudi Arabia, and they're actually pumping tons of seawater into their simple distillation plants, and then they are producing pure water out of it, and then they are using that pure water for domestic and industrial purposes. Before they can use it for domestic purpose, they actually add a little bit of salt back into the water so that they can convert that seawater into mineral water, and then it's drinkable for you. You go ahead and purchase that water as mineral water in the form of bottles and big containers, and then we use it. We can consume it. It's safe to consume
Okay.
it then.
So, what are the advantage of those? I mean, his process.
The main advantage of this process is you get both the salt and the pure water out of it. You're not just getting one ingredient, you're actually getting the both out of it.
Mm-hmm.
Since in
Okay.
crystallization, we wasted one ingredient, that was water. We only got
Water. Yeah,
salt out
because
of it, right?
because
But
it
in this
gets
case,
you up.
right, right. Okay,
Yes.
good. And this process is a little bit faster too compared to the previous ones, since you only need to start boiling the system. As soon as you start boiling, you'll start getting water.
Mm.
Although you're going to get it in
Okay.
the form of drops, and larger the system might take a larger time in comparison. But if you go for a fair comparison, you'll get both the products in less amount of time as compared to any of the previous processes. And that even pure, of course, right?
Yes.
Good, good. Moving on, fractional distillation. Fractional distillation, as the name suggests, is much more like distillation. I'm gonna actually zoom out a little bit so that we can see the whole thing a single go. Are the words readable now?
Yes.
So I wanted the whole diagram as well as the words in a single screen. Okay, fraction distillation, as the name suggests, is a type, also a distillation, but since the name fraction is there, it means that we are going to do distillation by parts. Every part would be known as one fraction. Why are we calling it like this? Since previously we were either trying to separate a insoluble salt from a liquid or a soluble salt from a liquid, but we never considered any miscible solutions. Now, as I've stated earlier, that miscible solutions are actually the ones in which a liquid can mix into another liquid. And it's not like every time, every example around us in which we only add solids to liquids, we may be mixing two liquids. We have taken many examples when we were going through this type, right?
Mm.
So
Yes.
talking about miscible solutions, if you have a mixture of liquids such as ethanol, it's a type of alcohol, the most important one at that, and water, it dissolve into one another. Now, ethanol and water are completely miscible. This means you can mix them together in any proportion and they will form a single liquid layer, not even two separate layers, a single layer. If the liquids are immiscible, they form two separate layers. For example, if you try to mix oil and water, they will form two separate layers. The oil will form the top layer and the water will form the bottom
Mm.
layer, because water has a higher density than oil. If you try to mix
Yeah.
ethanol and water, it would form a single layer and it would form a perfect solution. Ethanol plus water, since every part of this mixture would be both. Hence the
Mm.
word that you can mix together in any proportion and they will form a single liquid layer. Now you can separate them by taking advantage of their different boiling points. Water boils at 100 degrees centigrade, ethanol boils at 78 degrees centigrade. So this fractional distillation or distillation by parts is a really good idea. The only thing
Mm.
different from the previous distillation is that you'd notice that this area, the fractionating column as it states, has been addition to it. This heating system is the same, this flask is the same, the condenser is the same, this beaker is the same. What's different is this part. Now in this part, we have added a thermometer since we're going to require it
Mm.
this time, since we're going to work with two different boiling points. So it's important we have the thermometer and we have introduced a fractionating column. A fractionating column is a long piece of apparatus made out of glass since the glass is see-through, and we actually fill it up with little glass beads which are not shown over here, probably in the next diagram after this, I don't know, but they are filled like this all the way over here, right? Why
Mm.
do we do that?
Yeah.
We do that since slowly we're going to heat it up, and when the temperature gets to 78 degrees centigrade, we know out of these two liquids at 78, the ethanol will start to boil. So we'll get most vapors of ethanol over here, right? I'm
Mm.
going to show ethanol vapors by blue. We're going to get a lot of ethanol vapors over here, rising over here, all right, going through this over here, and even getting to this. Since this temperature is showing 78 degrees centigrade, so ethanol will be able to pass through, all right, and you'll get ethanol over here. What happens to water? Let me draw water with red. The water, which is drawn with red, would also go with some evaporation. Why evaporation? The boiling point hasn't reached yet. It boils at 100 degrees centigrade. The temperature is not currently 100, it is at 78 degrees centigrade. There would be some vapors of water over here, and they would also try to rise up. But when they
Mm.
try to pass through this, they won't be successful and they'll drip back into the same solution. Why? Because there is more temperature over here as compared to over here. In order to pass from here, the temperature has to be 100 degrees centigrade over here. Otherwise, they're
Mm.
going to condense at this temperature. Since the temperature is much lower than 100, they would condense along the way and they would drip back into the same container. They won't be able to pass through the condenser. What
Mm.
happens, since they're not able to pass through the condenser, we get almost pure ethanol over here. We don't get any water vapors over here. And what would happen? At 78 degrees centigrade, we'll get a beaker full of ethanol, and all of the ethanol from here would pass on to here. When the temperature
Yeah.
starts rising, it would rise to 79, then it would rise to 80. We need to quickly change the beaker and put new, dry, empty beaker over here. When the temperature
Mm.
gets to 100, the water vapors will also be able to pass. This time you're going to get water into the beaker, right? Pure
Mm.
water,
Yeah.
and that you will get at 100 degrees centigrade. This you collected at 78 degrees centigrade. So this time you get pure water out of it. So actually we call these fractions. This was the first fraction. This was the first part. Fraction means part over here. And this is the second fraction. So we get any number of liquids we have. If they have different boiling points, we can separate liquid by liquid, fraction after fraction. But you need to keep something in mind. The one with the lowest boiling point distills out
Yeah.
first. It would come out first. And the one with the highest boiling point, right, it's going to distill out last. So this one would be the last to come out, and this one would be the first to come out. Anything in between
Yeah.
will come out in between, of course. All right. Now, extension work.
Yeah.
Since I said earlier, this is filled with glass beads. And the same thing is written in the extension work. The fractionating column is packed with glass beads or something similar. Although the separation of ethanol and water in the lab works perfectly well with just an empty column for reasons that are beyond the international GCSE, a high surface area in the column, and the glass beads are only there for a higher surface area. What does these words mean? Let me tell you what these words mean. Now, we have glass beads filled like this, right?
Yeah. Mhm.
So anything which needs to pass through, and the ethanol and water vapors are going to pass through. And let's take an example of a water vapor passing through. It will need to move through this system in between the gaps, and this would take time. And during that time, it would automatically condense if the temperature hasn't reached yet. If it's at 78, the water vapor would condense and it would drip right back. For ethanol, it may leave the system because the temperature for ethanol is for it to get ripe and go all the way to the condenser into the beaker for collection, right? So a high surface area actually helps the separation by giving it more time. The ethanol produced about this experiment is 96% pure. Again, last 4% cannot be removed by the same fractional distillation, but that's beyond the requirements. This 96% is good enough for us. All right.
Yes.
Now, fractional distillation is a little bit more complicated than any of the previous processes. That's because we are trying to separate the things that can mix well into one another. Water and ethanol can mix well into one another. Be it 1 part water and 10 parts alcohol, 10 parts water, 1 part alcohol, same number of parts for both, anything, any combination you can come up with, we can separate them by fractional distillation to a very good recovery. Like 96% pure is good enough for us, right? So
Yes.
do we understand the whole thing?
Yes.
Remember, condenser works in the same way as it did in the previous experiment, simple distillation. So does the flask or the gauze or anything over here. One very important point that we need to understand is that, I'm going to erase all of it. The bulb of the thermometer should be right in the front of condenser's mouth. It can't be higher than this or lower than this. It needs to be right in front of the mouth of the condenser. Sure, so you are noting down the temperature for the particles that are passing through. If the thermometer is over here, the bulb is over here, it would note down the temperature of this point. We don't need the temperature for this point or for this point or for this point. We need the temperature for anything that is passing through. Hence, the bulb should be right in front of that. And the bulb is the bottommost part of the thermometer. I hope you know that already.
Yes.
Good, good. So these are the few things we need to understand about fractional distillation. We're going to study fractional distillation with some other examples with a lot more detail in upcoming chapters.
Yes. Okay.
So can I erase the whole thing, move on?
Yes.
Okay. So moving on, both liquids boil, but by careful heating, you can control the temperature of the column so that all of the water condenses in the columns and trickles back or drips back into the flask. Only the ethanol remains as a vapor all the way to the top of the fractionating column and out into the condenser. So by a little bit of care, we can actually separate carefully the ethanol and the water, which is pretty great. Since none of the previous processes were helping us with miscible liquids, this is the first one that helps us with this scenario. So filtration is for insoluble solids and liquids, and we get the solid, right? We also get the liquid, but they're not good. The purity is not good enough. For crystallization, it was for soluble solid. We never got the liquid out of it. Simple distillation was pretty good because it focused on the liquid, but we were also able to get the solid. But none of these were able to separate miscible liquids, but fractional distillation is, and with a pretty good purity. Make sense?
Yes.
Good, good. The next technique is going to be paper chromatography. And paper chromatography is a very good technique. Again, it's an easier one. The students can easily understand it. This, this is the last technique in the chapter. We will be able to end the chapter right after it. And I am going to go with this one in detail. We're going to practice many different scenarios in this case so that it's easier for you to solve the questions of paper chromatography. But we're going to do it in the next setting.